Hey guys, today we will be discussing the beta binomial conjugacy in that if we have a beta distribution as our prior, it'll also be our posterior for a binomial likelihood. It's kind of almost, it's a form of Bayesian inference because we will use Bayes' property, but it's kind of an iterative form of picking our best guess. We are trying to estimate some parameter data, say drug rate survival, and we have some idea about what it would be. We can put that in our prior distribution using our likelihood and get a better estimate with our posterior distribution, kind of gather more evidence, put it back into the prior likelihood posterior. So that's the sort of thing, and that kind of in general explains a little bit about what Bayesian inference is. So to put it into some more math terms, our first guess is our input, and we will say that this is a beta distribution with parameters alpha beta. So failure rate and success rate. And then our likelihood of the data given this parameter, so these many patients do well, these many patients do bad, for a drug with 60% good rate, and it will be a binomial distribution with n trials and beta as the chance of success. And what we want to show is that actually our posterior distribution, so given this data, the parameter could possibly be is actually in a beta distribution that's actually parameterized by the same set of parameters. What we kind of want to start doing is first appeal to Bayes' rule. We want to say, or first, it's probably a little bit cleaner if we kind of write our distributions. So this is the 1 over the beta function of alpha beta times our success, our successes by our success shape rate kind of thing, versus our failures minus our failure shape rate, which is more cleanly gamma alpha plus beta, gamma function, not gamma distribution, by gamma alpha, gamma beta, and then our same success and failure terms. And then our binomial distribution is also very well known, and that is the probability of choosing x successes out of n trials with the probability n. So usually NP, we have theta, so theta. Also, I think maybe it's a little bit important to note here, our input to our beta distribution is theta with fixed parameters alpha beta, but our input to our binomial distribution is x with fixed parameters n and theta. So just for clarity's sake, I'm actually going to replace this with theta here. So also very similar, so number of our successes, and then our number of failures. So now that we have these PMFs, we can kind of exploit Bayes' theorem here when we're trying to compute this f. So start saying that f of theta given x is g of x given theta times h of theta over the integral of the same term. So this is exactly restating Bayes' theorem for continuous distributions. And we also want to kind of look and see our bounds. I haven't put them yet, or our variable of integration. We kind of want to figure out what those are, right? So we just kind of think back to Bayes. So A given B is the same as probability of B given A times probability of A over all of our A values, right? So same as it B given A times A, probability. But and then we sum up over all of our A values. So in a lot of times this ends up being 1. So in our case, A is theta, and the range of values that theta can actually take on is from 0 to 1. And we'll be integrating over theta. And now we can just kind of plug in a lot of our PDFs. So G is binomial, and we know G is n choose x, theta to the x 1 minus theta n minus x, and then h is our beta prior. So our beta prior, if we wrote down here, was gamma alpha plus beta, gamma alpha, gamma beta theta, because that's our input to the beta distribution. Theta to the alpha minus 1, 1 minus theta to the beta minus 1. And we will be integrating this whole thing from 0 to 1. But the same thing, but just over all theta values. So let's rewrite. D theta. So now we have this gnarly expression. We are looking for how we can kind of simplify it. Obviously, if there are terms in the denominator that have nothing to do with theta, they won't integrate, and they'll just be constants. So this has nothing to do with theta on the top. This will go out, has nothing to do with theta. This has nothing to do with theta, it will go out. This has this can cancel with that. So we're kind of left with just theta to the x, 1 minus theta n minus x, theta to the alpha minus 1, 1 minus theta to the beta minus 1, over the same thing integrated, actually. And now, what we do here is we can really combine exponents of like terms. So theta to this, 1 minus theta to this, 1 minus theta to this, and the same thing here. And what we start getting is theta to the alpha plus x minus 1 by 1 minus theta to the beta plus n minus x minus 1. And because these terms are actually the same from the top to the bottom, we can kind of just copy that down to the integral. So alpha plus x minus 1, 1 minus theta beta plus n minus x minus 1, and then d theta. And what we can then actually kind of see here, so a little fact, and why I had mentioned this distribution being the inverse of the beta function of alpha beta is that the beta function has actually many forms. So what's really important here is that beta, let's say AB, equals we saw it earlier, so we'll see it every time when we write the beta distribution, but the terms are just flipped, so it's a gamma A times gamma B over gamma A plus B, and this also actually equals a very special integral. I think might even be called the beta integral of x times a minus 1, 1 minus x on the range from 0 to 1 of b minus 1 dx. And if we kind of look at how this is structured, something that goes from 0 to 1 times some exponent minus 1 is actually the same as this big integral we have down here. And this whole big integral can actually be reduced to the beta function of alpha plus x, right, minus 1, and beta plus n minus x. So this whole thing, it ends up becoming 1 over beta alpha plus x beta plus n minus x times whatever terms we have left. So theta to the alpha plus x minus 1, 1 minus theta to the beta plus n minus x minus 1. And this, as we know, is can be expressed as the gamma function. So we can gamma